Hello, everyone. In this section, we will introduce small signal analysis of BJT amplifiers, focusing on the common base and common collector amplifier configurations. In the previous section, we discussed the CE amplifier among the three basic BJT amplifier configurations. In this section, we will continue with the other two configurations, the common base amplifier and the common collector amplifier. The circuit shown here is a common base small signal voltage amplifier. The signal source is connected to the emitter terminal, and the load resistance RL is connected to the collector terminal. As before, we insert the T-model small signal equivalent circuit for the BJT. The resulting equivalent circuit is shown here. For this part of the analysis, we first ignore the output resistance RO associated with the early effect. We begin by finding the input resistance Rin. By definition, Rin equals Vin divided by In. Here it is also Vin divided by negative IE, because the NPN emitter current IE is usually defined as leaving the transistor, while the input current In is defined as entering the amplifier. The input voltage Vin is negative IE times Re, therefore Rin equals Re. Also, Re equals alpha over Gm, which is approximately 1 over Gm. From the equivalent circuit, IE can also be written as negative Vin over Re. After obtaining Rin, the input voltage is Vin equals Rin over Rin plus R sig multiplied by V sig. Once Vin is known, the emitter current can be found from IE equals negative Vin over Re. Then the small signal collector current leaving the output side is approximately equal to IE, or more precisely, alpha times IE. After finding the output side current, the output voltage can be calculated. The voltage VO is negative alpha times IE multiplied by the parallel combination of RC and RL. Since IE equals negative Vin over Re, VO becomes alpha times Vin over Re multiplied by RC in parallel with RL. Once VO is expressed in terms of Vin, the voltage gain is AV equals VO over Vin. For the common base amplifier, this gives AV equals alpha times the parallel combination of RC and RL divided by Re. Since alpha over Re equals Gm, this can also be written as Gm times Rc in parallel with RL. If RL is infinite, the open circuit voltage gain AVO becomes Gm times Rc. The overall, or global gain is GV equals VO over V sig. This is the input division ratio multiplied by the amplifier voltage gain, so GV equals Rin over Rn plus R sig multiplied by AV. Since Rn equals Re, this becomes Re over Re plus R sig, multiplied by Gm times the parallel combination of Rc and RL. Equivalently, it can be viewed as the output resistance term divided by Re plus R sig, with the alpha factor included. Finally, we find Rout. As usual, we set the signal source V sig to 0. Then IE becomes 0, so the controlled current at the output side is also 0 and behaves like an open circuit. In the output equivalent circuit, the test current is Ix equals Vx over Rc. Therefore, Rout equals Vx over Ix, which is Rc. To summarize the common base amplifier, the input resistance is Re, which is alpha over Gm and is approximately 1 over Gm. The open circuit voltage gain is AVO equals Gm times Rc, and the output resistance is Rc. Compared with the CE amplifier, the common base amplifier has a very low input resistance. Its Rin is only about 1 over 1 plus beta times the input resistance of a CE amplifier. This is not ideal for a voltage amplifier that requires high input resistance, because much of the source signal may be lost across the signal resistance. However, its open circuit gain is similar to that of the CE amplifier, and it has no phase inversion. In other words, the output signal and the input signal are in phase. Finally, the common base amplifier also has good high-frequency response. We will discuss this point later in the frequency response chapter. Next, we introduce the last BJT amplifier configuration, the common collector amplifier. This circuit is also called an emitter follower. The signal source is connected to the base terminal, and the load resistance RL is connected to the emitter terminal. Again, we insert the T-model small signal equivalent circuit for the BJT. The equivalent circuit is shown on the right. In this case, including the early effect output resistance RO does not make the analysis much harder. In the previous CE amplifier with RE and CB amplifier analyses, we ignored RO because including it would make the circuit analysis much more complicated for beginners. A complete treatment of RO will be left for electronics 2. In electronics 1, we include RO only when the circuit remains simple. In this CC circuit, RO is connected between the collector and emitter, and the collector terminal is directly grounded in the small signal circuit. Therefore, the collector side of RO can be separated and connected directly to ground without changing the output side behavior. As shown in the middle equivalent circuit, RO is in parallel with the load resistance RL. Now we analyze the small signal equivalent circuit using the T-model. We again start with the input resistance Rin. By definition, Rin equals the input voltage Vin divided by the input current In. Since the input terminal is the base, In equals the base current IB, and IB equals IE divided by 1 plus beta. The emitter current IE is equal to Vn divided by the series combination of Re and the parallel combination of Ro and RL. Substituting this into the expression for Rin gives Rin equals 1 plus beta, multiplied by the quantity Re plus Ro in parallel with RL. This is exactly the resistance reflection rule. The emitter side resistance is reflected to the base side by multiplying it by 1 plus beta. In small signal analysis, using this rule is a fast way to find IB or IE. After obtaining Rin, the input voltage can be found from voltage division. Vn equals Rin over Rin plus R sig multiplied by V sig. Once Vin is known, we look at the current path from the base input through the emitter side and down to small signal ground. Along this path, Re is in series with the equivalent resistance Ro in parallel with RL. The output voltage Vo is the voltage across Ro in parallel with RL. Therefore, Vo equals the parallel combination of Ro and RL divided by Re plus that same parallel combination, all multiplied by Vin. From the relationship between Vo and Vin, the CC amplifier voltage gain is AV equals Vo over Vin. Thus, AV equals Ro in parallel with RL divided by Re plus Ro in parallel with RL. Since Re is usually much smaller than Ro in parallel with RL, the voltage gain of a CC amplifier is approximately 1. The open circuit voltage gain AVO is the voltage gain when RL is infinite. Therefore, AVO equals Ro over Re plus Ro. Since Re is much smaller than Ro, AVO is also approximately 1. The overall gain is GV equals Vo over V sig, which equals the input division ratio times AV. Written fully, it is 1 plus beta times the quantity Re plus Ro in parallel with RL, divided by 1 plus beta times the same quantity plus R sig, multiplied by Ro in parallel with RL over E plus Ro in parallel with RL. In most cases, when R sig is not large, GV is also approximately 1. For the common collector voltage amplifier, the signal travels from the base to the emitter. In the actual circuit, the current through R sig is IB, while the current through Re and Ro in parallel with RL is IE, so these elements are not truly in series. However, by using the resistance reflection rule, the emitter side resistance can be reflected to the base side by multiplying it by 1 plus beta. Then all three terms are described by the same base current IB and can be treated as an equivalent series path. From this view, GV is immediately obtained by voltage division. The numerator is 1 plus beta times Ro in parallel with RL, and the denominator is R psi G plus 1 plus beta times Re plus 1 plus beta times Ro in parallel with RL. The same idea can also be applied in the opposite direction. The source resistance R sig, which is originally described by the base current IB, can be reflected to the emitter side by dividing it by 1 plus beta. Then R sig over 1 plus beta, Re, and Ro in parallel with RL are all described by the same emitter current IE and can be treated as a series path. Therefore, GV can also be written as Ro in parallel with RL, divided by R sig over 1 plus beta plus Re plus Ro in parallel with RL. Finally, we find the output resistance of the CC amplifier. We first set the signal source to 0 and then apply a test voltage at the output. Looking from the emitter toward the base, we can again use the resistance reflection rule. The source resistance R sig is reflected to the emitter side by dividing it by 1 plus beta, and then it is in series with Re. This series resistance is in parallel with Ro. Therefore, R out equals the quantity R sig over 1 plus beta plus Re in parallel with Ro. Since Ro is usually much larger than R sig over 1 plus beta plus Re, R out is approximately R sig over 1 plus beta plus Re. Now we summarize the common collector voltage amplifier. Its input resistance is 1 plus beta times the quantity Re plus Ro in parallel with RL. Its open circuit voltage gain is approximately 1. Its output resistance is approximately R sig over 1 plus beta plus Re. Since beta is usually large, around 100, R out is often close to Re. The overall voltage gain is also usually close to 1. Therefore, the CC amplifier has a high input resistance, a low output resistance, and a voltage gain close to unity. These are exactly the characteristics of a voltage buffer, which is used to solve input resistance and output resistance loading problems. For this reason, the CC amplifier is very suitable as the last stage of a multi-stage amplifier. It also has good high-frequency response, which will be discussed later in the frequency response chapter. This concludes the introduction to small signal analysis of BJT amplifiers, focusing on the common base and common collector amplifier configurations. Please look forward to the next lecture. See you next time. Bye-bye.